Okay, good morning everyone. My name is Dhruv Parmar and my group members Ashish and Bhushan. We all are going to give you presentation on our research topic of attention-based multimodal deepfake detections using facial dynamics and voice spectrogram features. Now this is our presentation outline. We have divided our presentation into different sections as introduction and motivation, problem statement, literature reviews and gaps, proposed methodology, data sets and evaluation metrics, expected results, conclusion and future ones. And about all of these sections we are going to talk in our upcoming slides. So, first of all, what exactly is deepfake? So, deepfake is nothing but it is like a AI generated synthetic media where persons is doing something or saying something which they actually never did in their past life. And this type of deepfake videos are generated using deep learning models, different deep learning models such as GANs and autoencoders. And because of these fake videos and audios, it is very difficult to detect what is real and what is fake. And because of that, these confusions, it can harm reputations of um, like politicians, known persons, spread misinformations and threaten national security. Now, why exactly we need multimodal detections? Why can't we just go with the unimodal detections and detect multimodal and detect deepfake media? Because if we see in present time, many deepfake detection systems are rely only on a one single model which is face. And like we can see that in present time our AI models, different AI models are upgrading, updating very much in small times. And because of that, this deepfake video creations models are also upgrading themselves. And because of that, it is very difficult to detect those present deepfake videos using just one like unimodal with unimodal systems. uh, so that's why it's a real edge come from combining what we really see and what we really hear. From that, we can detect from this both of the models. Using this both of the models, we can detect deepfake media. And that's why pairing facial dynamics with voice spectrogram, we it's like leads to more reliable and harder to fool detections systems. Now this is our problem statements where we want to say that like existing deepfake media detection systems are only rely on highly rely on single modality analysis, which is facial features. And it can easily be tricked by small or targeted manipulations. And because of this, it is very difficult to detect new and unseen types of defects. Because of these all reasons, we need multimodal detection framework that jointly analyze facial dynamics and audio spectrograms using attention mechanism. Now these are our motivation to do this research. First one is misinformation threat. Because of this deepfake video creations, it organized for fake news, political manipulations, and identity fraud at a very large scales. Second one is technical gap. No existing models or no existing latest research uh, jointly analyze facial dynamics and voice spectrogram with cross-modal attentions. Third one is security need. Digital forensics and media verification systems need lightweight, real-time, very fast deepfake detectors. Now these are our objectives which we want to achieve at the end of our project, end of our this research. So we want to make a model which like develop an attention-based multimodal deep learning framework, detecting deepfake using multimodal, which is like both facial dynamics as well as voice spec features. Second one is we want to make a model which optimize the proposed model for real-time deepfake detection with minimal computational overhead. Third one is we want to design a model which is like attention based which uses attention based mechanism that highlights audiovisual inconsistency and detect very accurate results. And the fourth one is we want to make a model which incorporate attention driven explainability for visualizing cross model feature alignment and enhancing transparency in deepfake media detections.
Hi everyone, I'm Ashish. Before getting into what we build, I want to spend a minute on what alternative out there because that's what motivates most of our design decision. This table covers 9 systems on the 6 years later. The first thing you notice almost all of them pick one modality and stick with it either facial analysis or audio, rarely both. First, face forensics by Osler, probably most cited benchmark in this space. Exception made on under the frame works well on a clean footage. The moment you hand it something from a behind, it won't train on accuracy drop. And there's no audio, so the whole audio forgery problem is just again. Digital and alternative emotion don't lie, it's a genuine clever idea. Real video has emotional synchrony. Your voice can match your face. Deepfake often break that. The builder Siemens shape around the 96.6 AU on the control database. But if some individual is just talking normally, no strong emotion. The method has nothing to hold on to. Right, 2023 to 24, we will move towards transformers, ABFS from all of it. 98.6% of PKV select dataset from number, but compute cost is high and it wants immediate on the dataset. That's the pattern across the board. Accuracy goes up, but so the complexity and cross dataset generalization stay the problem. Next, the table covers 20 papers in the total. I won't go through all it, but I want to pull out a few are directly relevant. Item number 3 was put in 2023 attention-based CMM assembled tested across 8 EV celeb dataset, BFDC and BFAMT multi-dataset evaluation, which is the right instinct. Catch if one modality is missing or degraded, corrupted audio, for example, performance drop noticeably. The system has no fallback strategy. Now, into number 7, BF transforms use it transform with a unique audio cross attention. Architecturally, it's the closest thing to what we are doing, but it's slow, not slow in a optimize it later way. Slow in a way that roll out real time development from the start. Next, on the second table entry, number 50 and 16, both 2025 papers, rank 5 with the transformer for voice deepfake, moving on them with the LSTM auto-encoder both around 97% accuracy, both audio and video. Both require large training set to generalize and within their value. Nothing to say about this. After 20 papers, the gap is clear. Nobody has combined temporal facing modeling, image spectrum, audio processing, and Cross-modal attention is one system that also light is put on real time. That's what we are trying to do. Next, there's a three problem indices we can have to solve. In one of them is first single modality. Most detectors look at the face, nothing else. The possible to only manipulate the video track doesn't produce audio artifacts. So an audio only detector is it entirely. And the reverse is true. But here's the thing. Real speech has a very tight coupling between lips, meaning facial muscle activation and positive output. When you generate a deepfake, that coupling is hard to figure out perfectly. If you are only watching one channel, you are throwing away half the signal. Second is no temporal modeling. A lot of systems analyze them individually, each one like a photograph that missed or a deepfake actually fake. The problem isn't usually in a single frame, it's in the motion pattern across the profile. A jaw that looks slightly down during a vowel or blink with a bad angle, you only see that in a sequence. The Bi-LSTM is our visual stream is specifically there for the reason. Third is computational fusion. Several papers will model and video by just tagging the feature vector and passing them to class that treat every frame and every frequency band equally. They are not equal. Some movement carry for more inconsistently than others. Cross-modal attention learns which part of each stream to use dynamically based on what other stream is doing. That's meaningful difference from concatenation. The next is support methodology. Two stream, one fusion layer, one output near each partner. Visual stream. We decode the video at 20 fps with a FFMG MTCM. It takes a face of each frame and crop it to 54 by 54. Thus, we have 60 frames at a time. 8 frames straight go into 3D CMN using uh, C3D backbone. Standard convolution accurate planner. Started dimension only C3D adds the temporal dimension. So the kernel is 3D and it sees across frames, not just within them. The output of that goes into via LSTM two-layer hidden size 56 which reads the sequence forward and back. Final representation we lies in on to the T time by 5 to its encoding of the face image, not just what it looks like. Second, audio stream run in parallel. We extract the audio at 16 motors apply and SPFL 15 25 ms humming windows 10 millisecond out and map it onto ET-mel beta bank. The result is a main structure and patch that cover equal to the same time window as the window segment. So the two screens share a temporal axis. The spectrum goes through 2D CNN 4 convolution block from self-attention model with 8 head the attention normal which time steps carry the strongest deep signal in practice that tend to be for meant transition moment where voice conversion artifact shows up most clearly and quickly. Feature vector fusion multiple V and A are projected into a shaded to 52 dimension space through normal linear layer. Then cross-modal attention run PQV or A to find which angle moment corresponds to each individual and 8 images need to do because this simplifies the system actually detects the classifiers. It's comparing corresponding movement across modalities, not just mixing feature vector. The fields output goes through a filtered FC layer drop out at 0.4 and the supplements that might be real or fake from confidential. When computer is low intentionally, the system can be paralyzed for a real-time interface. Most transformer-based competitor cannot claim. Next to dataset, is the 10 dataset we analyze for training model. First is the AKV, which has found red video. This is the one way to most CV in our evaluation space that analyze conversation data rate and independently so you can't detect fake by looking at just one channel. Model that ignore audio frequency. For this forensic, the 500, 5000 videos, 4 in 15 permanent some method completely labeled the standard benchmark and reason which they use it was data set questions. We need user number on F++ to compare against this literature. The rest is that model work is exactly what we don't use it as our only test. That's the literature. The three gaps we found in it in the architecture we designed around those gaps and the dataset will be evaluated.
This slide explains the dataset and prerequisite steps used in our project. For training and testing the model, we collected data from multiple deepfake datasets like face forensics, fake AVC, hyper forensic, and other AI integrated video datasets. This dataset contained both real and fake videos in formats like MP4, MOV, and JPG. Using multiple datasets helps improve the model's robustness because the system learns different types of data instead of depending only on dataset. After collecting the data, reprocessing is very important because raw videos are not directly suitable for training deepfake learning models. So first we converted all videos into common format using the filters. So here are the 6 steps. First one is a format conversion, second frame extraction, third quality filtering, fourth face detection and crop, fifth resize normalize, six audio reprocessing. So first, we converted all video into common format using FF, FD. Next, we extracted frames from videos using compressing. Then low quality blur to widgets and corrected frames were known to improve data quality. After that, face detection and face proofing were performed using MTCNN and so the model can focus only on facial regions. All images were resized to 224 by 224 pixels and normalized between 0 and 1 for consistent framing. For audio processing, we extracted spectrogram features using Reversa and STFP APIs. Finally, after processing, we obtained standardized facial image and audio spectrograms, which are easily input in our multimodal defect detection system. This slide shows the performance comparison between existing models and our proposed models. We compared models using accuracy, AOC, ROC, and difference score metrics. Multi-potential and fake AVC lab baseline models improve multimodal detection but still face limitless inconsistencies. Exceptional achieve the very high accuracy on face forensics, but it mainly focuses only on facial features. ID will also perform well on C-lab dataset. Our proposed model achieve around 91.2% accuracy, 0.984 AUC score, and 0.952 FS score. The main advantage of our model is that the combined facial dynamics and voice spectrogram features together using cross-modal attention. Because of this multimodal approach, the model becomes very reliable and difficult to full compare to single modality systems. So now slide graphical analysis. In this slide, graphical comparison of different defect detection models is shown. The first graph represents accuracy comparison. Here we can see that exception net gives very high accuracy on control dataset, while our proposed model also gives the strong performance across multiple datasets. The second graph shown AOC ROC comparison, which also known as area under curve. Our proposed model achieved one of the highest AOC scores, which means the systems can effectively separate real and fake videos. The third graph represents reference score comparison. Our proposed model achieved a high reference score because it balances both precision and recall properly. Overall, this graph shows that combining facial and audio features improves deepfakes detection, performance, and robustness. So, to this slide, evaluation matrix. This slide explains the evaluation matrix used to measure model performance. Accuracy tells us how many predictions are correct out of all tested videos. AOC ROC measures how well the model separate real and fake videos across different threshold values. Higher AOC means better performance. It was for importance because it balances precision and recall together. Here or equal error rate represent the point where false positive and false negative becomes ignored. Lower ER means better detection quality. Precision tells how often the videos played as fake are actually fake. Recall tells how many actual fake videos are correctly detected by the system. Our target performance is accuracy above 97%, AOC above 0.97, reference score above 0.94, and ER above 5%. To conclude, our project proposes an attention-based multimodal deepfake detection system using facial dynamics and voice spectrogram features. Unlike traditional systems that only analyze facial images, our model combines both video and audio information together. The cross-modal attention mechanism helps detect inconsistent between facial movements and voice patterns. This improves robustness against advertised attack and unseen deepfake types. That proposed systems is scalable and can be used in real-world applications like digital forensics, media verification, and cybersecurity. This slide contains the research paper and references used in our project work. We refer to multiple papers for deepfake detection, multimodal learning, transformer models, and audio-visual features. These studies helps us understand current challenge limitation of existing systems and advanced detection techniques. Progress also helps us identify research gaps and design our control mechanisms. This slide contains continuous of trans related to transformer-based models, audio with detection, multimodal feature, and several papers. We also study datasets like KKVSLab and methods like eye blinking detection and audio deepfake analysis. These references provide strong support for our research and implementation. Thank you.